Welcome to this lecture of calculus. In this lecture, we shall state and prove the Darboux's theorem. The Darboux's theorem, as stated here, states that if there is a differentiable function defined on a closed interval ab and k is any real number that lies between f dash of a and f dash of b, then there is at least one real number c in the open interval ab such that f dash of c is equal to k. Before taking the proof of the Darboux's theorem, we shall first recall the conclusion of the intermediate value theorem that we had proved in the previous lecture. So here we state the intermediate value theorem. The theorem states that if f from AB into R is continuous and there is a real number k such that f of a is less than k is less than f of b, then there exists a real number c belonging to the open interval ab such that f of c is equal to k. Now here if we compare the conclusions or the statements of the intermediate value theorem and the Darboux's theorem, so we can think of this Darboux's theorem as a kind of an intermediate value theorem for the derivative of a function which is defined on the closed interval ab. So this was just a sort of a relationship here. Now before again going into the proof of the Darboux's theorem, we shall explain something as how a function or what are the pointers at which a function can possibly assume a maximum value or the minimum value. So that is here हम ये एक्सप्लेन करना चाहेंगे कि एक फंक्शन किस पॉइंट पे पॉसिबली उसका मैक्सिमम हो सकता है या पॉसिबली उसका मिनिमम हो सकता है, तो उन पर्टिकुलर पॉइंट्स की किस तरह की प्रॉपर्टी होगी इफ आवर फंक्शन इज कंटिन्यूस और डिफरेंशिएबल. Now here let's try to do this with the help of this graph. Let's randomly choose a function here. So suppose we have a function that starts like this. So let's have this function from this point which is a, and now let's take up to this point which is suppose this is equal to b. Then the possible points at which the function assumes the maximum or the minimum value, it is something like this. So we have this function where the function goes very up, so it has a large value, and similarly this is a point where the function goes very up and it has a large value. Similarly this is a point and this is a point, and these are certain points where the function possibly has some largest value or the smallest value. Now this value can be defined in this way. So this height of this point from x-axis to this point, this height is the functional value f of let's take up x naught, and similarly this height is the value f of x1, and similarly this height is the value f of x2, and similarly this height is the value f of x3, and this height is the value f of x4. Now these are the points. Now we can see this is the point where the function has the largest value. So at this point f of x is maximum, and similarly at this point f of x is minimum. That we can see from the graph of this function. But now what are the properties of these functions? What are the properties of these pointers? Both of these pointers have one similar property, that if we draw a tangent at this point, it will be parallel to x-axis. And similarly, if we draw a tangent at this point, this will again be parallel to x-axis. And similarly, even the tangent at this point is parallel to x-axis. And similarly, the same property for these 2 points. So therefore, one nice property that we have for a point where a function can possibly have a maximum or a minimum value, those points are the points at which the tangent to the function must be parallel to x-axis. So thus the points at which a function assumes the extreme values have the property that the tangent must be parallel to x-axis. Now the tangent is parallel to x-axis. This in terms of the functions means that is f dash of x is equal to 0 at such point. Now keeping this property in mind, we can easily prove the Darboux's theorem. So now let's begin with the proof. So we are given k is a real number such that k lies between f dash of a and f dash of b. Now here we have two possibilities. One possibility is we have like f dash of a is less than k is less than f dash of b. The other possibility is f dash of b is less than k is less than f dash of a. The proof for both the possibilities will be similar. So we assume without loss of generality, assume without loss of generality that f dash of a is less than k is less than f dash of b. Now define a function g of x which is defined as f of x minus kx. Then g of x is differentiable because f of x is differentiable as well as k of x is differentiable. So therefore g of x is differentiable on interval a comma b. The reason for that is because both f of x and the function kx are differentiable on the closed interval a comma b, and we have this g dash of x is equal to f dash of x minus k. Then let's compute the values of g dash of a and g dash of b. So then g dash of a, this is equal to f dash of a minus k, and similarly g dash of b, this is equal to f dash of b minus k. Now as we have assumed that f dash of a is less than k, so therefore f dash of a minus k, this is less than 0, and we have f dash of b is greater than k, that is f dash of b minus k, this is greater than 0. So we have g dash of a is less than 0 and g dash of b is greater than 0. This means that the function g of x is decreasing at x equal to a, and the function g of x is increasing at x equal to b. As g dash of a is negative at a, so this implies g of x is decreasing at x equal to a, and the same function g of b, as it is greater than 0 at a, so this means g of x is increasing at x equal to b. So therefore what we have a situation that the function is decreasing at x equal to a, so we can have this kind of a situation. So suppose this is a point a here and this is a point b here. As the function is decreasing at a, so therefore the functional values are decreasing like this. This is a point at x equal to a. So this means the minimum value of the function cannot be attained at a. Now at the same time, the function is increasing at b. That means at the point b, the function goes like it goes upwards. So therefore, at the same time, the maximum value of the function cannot be attained at the point b. So this means the maximum value or the extreme value, this implies the extreme value of g of x must be attained at some interior point, must be attained at some interior point, say C, which belongs to the open interval AB. So therefore we have a point C that belongs to the open interval AB at which g of x will attain its maximum value, or in fact also the minimum value. Now at this extreme value, we already know that a function will attain its extreme value at a point, then the derivative at that point must be equal to 0. So at this point we must have this g dash of c is equal to 0. But g dash of c equal to 0 means f dash of c minus k is equal to 0. So this implies f dash of c is equal to k. Therefore we have found a point c belonging to the open interval AB such that f dash of c is equal to k. So this is how we prove the Darboux theorem, and this completes the proof.